Well, good afternoon and welcome to today's CAUSE Journal of Statistics and Data Science Education webinar. Our focus today is Bayesian methods and the statistics and data science curriculum. And I'm really excited to have Jingchen, Monika Hu, Colin Rundel, and Kevin Ross sharing some of their expertise and talking a little bit about some of the papers that were published in the special issue. I'm pretty excited about this topic just because the changes in computation and the restructuring of the undergraduate and graduate curriculum has opened up great opportunities to be thinking statistically in various ways. And I think the Bayesian approach is really compelling for that. I need to start off by acknowledging that I'm an empirical Bayesian, or what the Bayesians would call a wishy, livered frequentist. But I see the value in Bayesian methods to really structure problems. I first saw this when I attended a workshop in graduate school, and it was pretty straightforward to kind of take a random effects model, where normally we assume that the random effects are normally distributed. What if we allowed them to be t-distributed? That becomes a mess from a frequentist standpoint, but it's very straightforward to be thinking about in various ways. Recent decades, we've seen a lot more happening. What was previously just a kind of an advanced graduate course now showing up in the undergraduate curriculum. And I'm really very excited to talk about that today. Let me briefly introduce our speakers. Each of them is going to be talking briefly about some topic as part of the overall cluster of papers. And then we'll have a general chance for some Q&A as well as from the audience. The link to this special issue, the cluster of papers, I've just put in here. It was the last issue in 2020. We'll get started. So Jingchen Monika Hu is an assistant professor of mathematics and statistics at Vassar College. She teaches an undergraduate level Bayesian statistics course, which is shared online across several liberal arts colleges. Her research focuses on dealing with data privacy issues by releasing synthetic data. Colin Rundel is a lecturer at the University of Edinburgh, as well as a professor of the practice in statistical science at Duke University. His research interests include applied spatial statistics with an emphasis on Bayesian statistics and computational methods. Last but not least, Kevin Ross is an associate professor of statistics at Cal Poly San Luis Obispo. His research interests include probability, stochastic processes, and applications, as well as probability and statistics education. Last but not least, I'm Nick Horton from Amherst College. Wanted to first begin by just briefly mentioning we have some other upcoming webinars in the CAUSE Journal of Statistics and Data Science Education webinar series. Next month at this time, we'll have Mina Doshus and also Albert Kim talking about playing the whole game and data scraping for fun and profit. In April, we have a webinar on what makes a good statistical question. The sign up and other information for all the webinars are available at this link. And as is our usual practice, all the webinar slides and recordings will be available at that link. This webinar is being recorded. One big plug for CAUSE, and thanks to CAUSE, the Consortium for the Advancement of Undergraduate Statistics Education. They're making this all possible. They're also organizing the US Conference on Teaching Statistics 2021, Expanding Opportunities. The registration will go live for this sometime, I would imagine, in March. There is an opportunity to get on that program with the posters and beyond. That information and submissions are due on March 11th for those looking for feedback on your posters or your posters and beyond presentations. Definitely check it out. The price is right. It's really exciting things going on there. And so that's kind of other CAUSE related announcement. So let me talk briefly about the Bayesian cluster. This included 5 papers, one of which was a book review that was published in the last issue of the last year's volume. And it started off with a paper by Andrew Ho on why Bayesian ideas should be introduced in the statistics curriculum and how to do so. There was Monika's paper on the Bayesian statistics course for undergraduates, Bayesian thinking, computing, and research. There was a paper that she co-authored with Jim Albert on Bayesian computation in the undergraduate statistics curriculum. There was a review by Jim Albert of the Statistical Rethinking, a Bayesian course with examples in R and Stan. It's interesting to me that I understand that that's one of the best-selling books that CRC Press has published in recent years, and it's had really wildly popular, particularly in client disciplines that do a lot of statistical modeling. And then last but not least, there was a really informative panel discussion with Lisa Johnson, Colin, Jingchen, Kevin, and also Alan Rossman. And so those comprise the special issue, and we just thought it would be nice to kind of be thinking about talking more about some of these questions. So we organized this conversation today. So Monika, do you want to start off by talking a little bit about some of your work?
Sure, thank you, Nick. And I should also say I would thank Alan Rossman for organizing the panel discussion paper, as well as Jeff Whitmer to, I guess, make sure that all of the papers appear in the Bayes cluster finally. So yeah, so I would like to introduce you a little bit of the upper level statistics elective course at Vassar College, upstate New York. So this is a 300 level course. Like I said, it's an elective. So it's not required for any major, but many of our majors, and in particular, actually also we have a cognitive scientist who is a Bayesian cognitive science on campus. So we have actually a lot of students from that program taking this elective after they complete the prereqs, which include the multivariable calculus and probability. And because of the way that Vassar, we structure our stats curriculum, we do not require prior statistics course exposure before taking this course. And also because of that, like no programming is required as well. But then of course we have to do a little bit catch up for everybody to make sure that everybody is ready to take the course, or at the beginning of the course, so everybody's on the same page. So to give you a sense of the topics that we cover, there are three big components. We talk about inference. Bayesian inference in particular will have prior, posterior, and posterior predictive. And the computing is an important aspect, I think, not only in my course, but every other Bayesian course out there. And for us, we use MCMC estimation with JAX, okay? Which is a pretty convenient interface, and you can use it in R or Python. But for our course, we use RJAX. And the third component of the course is applications. Okay, so we have the particular methods that we cover include hierarchical modeling, regression, and latent class modeling, which are like what Nick was saying earlier, is really in some way easily done in the Bayesian framework in many cases. So we really want to get the students exposure to those topics. And then in the context of what this kind of methods or applications introduced, we use various examples such as like student dining preference surveys, some drama ratings data set, consumer expenditure surveys from the Bureau of Labor Statistics, as well as student test scores, just to get a sense of a wide range of data sets that people can work with. And then of course, many of them are very suitable for hierarchical modeling, regression, and latent class modeling. Nick, can we go to next? Yeah, so my second slide here is really just my features and recommendations of the course that I really want to mention to you all in really in this time. And so I really found useful, and I think Kevin uses that in his course as well, is doing case studies where like we will have students work on advanced topics or like a new applications, but then it's usually towards the end of the semester, and then they're able to introduce, we're able to introduce them to new methodology out there that they might never thought about before. But by the time that that they have covered, we have covered the computation as well as the basic modeling, some models such as the latent class model in some cases will be more suitable for a particular data set than whatever they have done before, such as hierarchical modeling. So those are the case studies that we're able to introduce. And in particular, I really highly recommend, if there's a really interesting case study that you think can bridge the gap between one model to the next, I would recommend doing such case studies like twice. Like introduce it first, let students get to expose, and then try to use whatever they have learned so far to do it. And usually that's a quick run. And then when you go over it in class, you're able to point out, like say, hierarchical modeling has certain like limitations in this case, and then what about this? And then by that time, I think once we add like say sample code of JAX, and then people will, I think, gradually get used to it. So my experience so far, I think, is that students are really excited in doing this kind of like a bridge. And then once they have enough material to get them started, I think the second round of the take two case study will just like go pretty smoothly. And I also put the discussion forum in the parentheses next to it. So I use Moodle. So we use Moodle at Vassar, but any LMS, if you want to encourage discussion and then interaction, I think like posting those questions and then use discussion forum interactively. I guess now in particular, everything is remote and online under the pandemic, I think is ever more important now. And the other thing I want to mention is that because this is an elective course, and then I encourage students to read, like try to get some exposure to journal articles. And I found certain articles out there that, for example, like journals like the American Statistician, where they have nice short article that goes over the concepts of many important things, but as well as designing like really neat simulation studies that able to demonstrate how things work. So I found those kind of stuff really useful to be introduced to students. And in particular, I encourage and recommend like providing a reading guide where you can have like a list of questions. Some of them are really just going over the key concepts in the paper, or like some mathematical derivation to make sure that everybody understands it. Or some others is like really just talking about, like say in our case, because it's a Bayesian talking about give sampler, it's really just like how many samplers they have run. And then like, can you identify it from the paper, things like that. So that kind of reading guide together with discussion forum is really useful, I think. And then you can really get students thinking about how to read the paper, how to critique the paper. And then in particular, the one that we love reading is actually coming from 1990, I think, when Gibbs sampler was first introduced. So there's so many different, I think, new things being happening afterwards. So there could be many good discussion about what's being done back then and what's being done now and which one is better, or maybe nothing is better, but at least we see the differences. Lastly, for those type of articles where they have simulation studies, I highly recommend also to design a computing lab around it that is really like walk students through the details step by step, and then they can replicate it and they can really see how those figures are produced. And maybe now with ggplot2, everything looks even better. So anyway, I think that like wraps up like the whole journal article reading. And I do notice that once students are exposed to like reading journal articles, they're actually going to venture to read more articles for their projects. And then I think that's a really good encouragement. I think also like get rid of the barrier for students thinking, oh, reading articles is so high level, I might not be able to do it. But once they get into the rhythm, I think it's really doable and good. So I include the GitHub repo of the course where I have the material. I will later put it into the chat as well. And also Jim Albert, I think, who's in the audience, and we had a probability and Bayesian modeling book published in 2019. Yeah, I show you the link as well as the cover. So it's designed for a 2-semester sequence, sort of like not replacement, but like sort of like replicating how a traditional math stats course where you have a probability and then frequentist classical inference, whereas this book is trying to think in a different way of doing probability, but then also doing the modeling from the Bayesian perspective. Yeah, I think that's all I have. Thanks, Nick.
Monika, that's great. And again, lots of great kind of teaching strategies and ideas. Particularly find the idea of getting the students to be reading those papers as a way for them to kind of be thinking about how they're going to learn other things once they don't have the benefit of you as their instructor. For the audience, got questions for Monika, for anybody? The Q&A panel is open. You can start to kind of submit questions there, but I'm going to turn things over first to Colin, who's going to be talking briefly about the Bayesian Elective at Duke.
Hi, everybody. So I'm going to talk a little bit about a course that I've taught a handful of times at Duke as sort of what I would call sort of a follow-on course to an introductory Bayes course. And that's sort of the role it played at Duke. So this was a 4th-year elective course that was offered to the undergraduate students. And at the time, that was also our master's program was fairly new and growing, and we were looking for 2nd-year electives that were sort of topic specific as well. So this fits sort of this nice space of what can we do that will build on the Bayes course that both of these groups have already taken, but then give them some more sort of applied job skills type class that will also then reinforce some of the other things like computing and everything else. So this course is a spatio-temporal modeling course, which is mostly to say we spend a lot of time talking about time series, a lot of time talking about space, and then a little bit of time talking about when we combine the two, it gets really hard. But both of those are areas that students are just fundamentally interested in. There's lots of data that they can think of and come up with. And it's also something that's fundamentally missing from a lot of their earlier classes. We talk about, okay, we make these IID assumptions, but we don't often talk about what do you do when it falls apart. And this is a very nice and easy case to talk about, okay, there is a correlation in our data, but it's something that we can actually use to our benefit. And how do we go about doing that? And so that's sort of a central through line of the course in terms of thinking about things and where it sort of fits. So generally, the structure-wise, 15-week course, it's on semesters there. It's an elective, so not everybody takes it. 15 to 25 students, roughly split between the undergraduates and the master's students. And they're roughly sort of fourth year undergraduates and second year MS students as they go through. We very much sort of required and depended on the fact that the students went through Duke's Bayesian course before. That's a very traditional Bayesian theory course that goes through all of the basics of conjugate and prior, posterior, and all that. Conjugate models, basic MCMC, Gibbs, Metropolis, Hastings. But it tends to err on the side of being a little bit sort of toy examples, not a lot of real data analysis, that kind of thing. And even then, that's a very full course in 15 weeks. So it's hard to get through all of that content. And so very much the view here is saying, okay, you've gotten that. Now let's assume that you know what MCMC is. You may not have all the details down, but you have a basic idea. Let's do this and use it for something practical and see what we can come up with. We're also able to benefit a lot from the fact that students are coming in with other courses. So the intro data science course, the regression course now has our statistical computing course. So we can also count on the fact that these students mostly know some basic R, and we can proceed from that as we go. And so again, like Monika, we leverage JAGs and R to do almost all the computation. And very much this course is sort of equally spread between sort of a third theory, a third applied modeling, and a third computation. And we sort of rotate between those with the various topics as we go through. And again, I think all of those are necessary and important parts of this, but we don't want to give any of them sort of short shrift as we do that. It is Bayesian primarily, and partly because that's my own bent for all of this. It's how I approach these kinds of problems. But I'd also really strongly argue that it gives you one of the most consistent frameworks to approach all of these different kind of modeling tasks. Like we use exactly the same sort of formulation. The JAGS code looks remarkably similar as you go through all of this. Versus if we're using a more traditional frequentist approach and maximum likelihood, we could do it, but I think there'd be a lot more contortions in terms of making all of this stuff look the same and showing that commonality between the approaches as we go. And so I think that's one of those really big wins that we get here. But we don't want to be dogmatic about this. We want to show them the various approaches, show the various tools, and get towards getting a result as quickly as possible and doing something useful with that. So as I mentioned, R and JAGs are the primary thing. There are a handful of cases where the computation gets a bit rough. JAGs is too slow to do some of those things. It's not a great experience for the students when they're sitting there for an hour waiting to see if their chain converges. So we do some stuff with STAN just to show them how that works. And then there's also some very important like domain-specific packages like SPBayes for fitting Gaussian process models that is unfortunately orders of magnitude faster than the alternatives. So it's a different kind of burden to teach that, but the benefits outweigh the cost. But that's the kind of thing that's also important to keep in mind as we go through all of this. And I guess where I'll leave this off is to say that this is the version that's been taught previously up until about 2018 before I was on leave. I'll be back at Duke in the fall, and we're going to be offering a new version of this course, which is based on the number, a 300 level version of this course. So we won't have that Bayesian prerequisite. I still plan to make this a Bayesian course, but we're going to have to restructure what we depend on and what we expect the students to know. But I think this is an interesting idea because it's going to open it up to a wider audience. We're going to be able to get minors in. We're going to be able to get students from other majors in, not just sort of our capstone students just before they graduate. And I think that's going to be a useful experience for me as well as for the students, hopefully.
Great, Colin. Thank you. I'm pretty excited about that aspect of that you're teaching an advanced modeling class here with a coherent framework that can be kind of tweaked and adjusted as you go. And I think that's a pretty exciting aspect of this. Kevin, last but not least.
Sure. Thank you, Nick, for inviting me and organizing this, and thanks everybody for attending. So let me tell you about our Bayesian Statistics class at Cal Poly. This class, it's the 4th year that it's being offered. I'm currently teaching it right now. Alan Rossman taught it the first time, and I've taught it the 3 times since that. At Cal Poly, we're on the quarter system, so we have 10 weeks courses. It's an elective course. It's not required for any program at Cal Poly. We have about 25 to 30 students per year, but it has been growing. I think the first offering had 20 students. this quarter I have 33 students, and our elective courses are capped at 35 students. So we're pretty much at capacity. There does seem to be a lot of interest from the students. The majority of students are statistics majors, though I do get a handful of students from other scattered departments, economics, business, life sciences, engineering, and a couple master's students have taken the class. The prerequisites are Stat 1 and Stat 2, and then our first course in probability, which has single variable calculus as a prereq, and it has a computer programming prereq. It's not the typical probability course that you might see in the first half of a probability and math stat sequence. It's a little bit more applied. It has a lot more emphasis on simulation. No prior experience with R is required, though most of my students have seen R before, and they do have a computer programming prereq. So I found that if I ask students to install R in RStudio, they have no problem with that. If I hand them an R Markdown file, they have no problem running and tweaking it. So I haven't really had to teach too much, intro level programming. I can kind of just hand them things and they're able to deal with it. Nick, would you mind? Thanks. So this is not the way that I've been teaching the course, but my kind of vision for this course is that ultimately it will lead to a Bayesian version of an intro stat class. Now, we do have a probability prereq. So in 10 weeks, I kind of have to assume that students are familiar with probability. We do have a statistics prereq. So I can assume that students are already familiar with statistics. But in terms of the methods that we cover in the class, we don't really go very far beyond what you would go through in an intro stat sequence. So, we cover 1 and 2 sample procedures, we cover regression. We do a little bit with hierarchical models, which, is not something that they would have seen in their intro stat class. I can put the links in the chat later. You can see the course topics in the link there. And I do have some notes that I've been updating as I'm going through the course this quarter, which are available in a book down, which you can see if you want. But I really think of the class as kind of a Bayesian version of Stat 1 and Stat 2. So we do some comparison of Bayesian and frequentist methods as we go. As Colin mentioned, not to say like this one is right and this one is wrong, but to talk about advantages and disadvantages of different approaches. And to talk about how students, what we're trying to do is just give them a broader set of tools that they can use when they approach different problems. In terms of computing, we use R and we do MCMC and we use some JAGs. The first half of the course, we primarily focus on one parameter models. And I try to do a lot with Bayes table type calculations, just spreadsheets and discrete priors and things like that. So, from that perspective, they're not really doing a lot of coding during that part of it. It's really just kind of this table type calculation. But one thing that I've started doing, and then we get to MCMC, and then we start using JAGs. So I found that when I was teaching this course in the past, the first 5 weeks would be fine, and then once we get to multi-parameter models, the level of difficulty just really ramps up. So what I've tried to do earlier this quarter is, even when we're talking about one parameter models, even when we're talking about conjugate priors, introduce the JAGs code earlier, and just to give them something to run, to say, we already know how this works, but just to get them used to the computing. And I think that's helped bridge the gap a little bit.
Great. Well, thank you, Kevin. And we got some kind of questions and things coming through the Q&A and through the chat. I guess I'd like to take my moderator's prerogative and ask a couple of questions of the panel. And the first one, ask first to you, Monika. Was there something you learned or you found surprising from the cluster of papers, like as you read them all together?
Yeah, right. So because I'm involved with a couple of papers here, so I guess the most stuff that I learned, well, I guess one thing is the panel discussion paper. I think I learned a lot of how different approaches people have taken. So it's in addition to me, Colin, and Kevin, there's also Alicia Johnson from Vassar College, and she teaches a Bayesian course for many years by now. I think it's a capstone course. And I think one thing, and I know Nick will ask the question again, is about the computing, because I realized that all of us, maybe the three of us here actually use JAX, which we discussed a little bit in the chat, but I think Alicia uses RStan and STAN interface. And then I think that particular discussion about like what to choose for your course, and then what kind of, what is the level of coding, as well as like the understanding of the code that is required going into each course, I think heavily influence how we're going to choose the computing. So I think it's, I guess not surprising, but I think it's definitely like interesting to learn different aspects. And I think one of the questions asked here, how about even more basic undergraduate course without a calculus prerequisite? To me, well, Kevin is probably a better fit to answer that question, but in my mind, like say, the reason why I picked JAX for the computing is more about, I think I want the students to understand the model, like say how you can write the syntax. And I think many of us choose it because of this. But as I understanding STAN, in particular, certain packages like RStanArm and BRMS, those RStan packages, I think they can, their syntax is really similar to like they have a StanGLM, which is very similar to the syntax to a GLM when you run it in R. And I think in those cases where if we do not require calculus as a prerequisite, and then that kind of like packages as well as like understanding the model, I think will be really useful from the from that kind of perspective.
Great. Colin?
I think, yeah, just partly being part of the panel was super fascinating just to see how similar a lot of the approaches are across the board, and sort of its convergent evolution in some sense of like all of us sort of messing around and playing with these things and seeing what we come up with. And I think that's sort of reassuring in some sense that it's like, okay, I'm not the only one doing it this way. I think it's also really reassuring. Statisticians of a certain generation tend to treat the frequentist versus Bayesian divide as this like holy war, and blood was spilled over this. And I appreciate that people fought those battles, but I feel like a lot of younger generation are coming in with a much more sort of practical attitude to all of this of, let me just do what works. And I think for us, particularly within this panel discussion about education, I think we can make a compelling case for the Bayesian approach because of the educational approach, because there's advantages to this. There are difficulties and there are some complications there, but I think we can make a pretty compelling case there. And that's one of those things that I came away with from the panel discussion of like, yes, we're all coming to this sort of same conclusion here because of that idea.
Yeah, and I do like that we've emerged beyond the religious wars of that previous century. Kevin?
Sure, yeah, I think one thing that I was surprised about was just how many resources are available for teaching Bayesian statistics at the undergraduate level. I know when we were first proposing this class at Cal Poly about 5 years ago, even then it was hard to find things at the level of what we wanted to teach, you know, something that was more applied, not theoretical, didn't have a lot of mathematical prerequisites, didn't have a lot of computing prerequisites. So, you know, Monika's done a great job of, you know, curating materials. She has a GitHub where she has a lot of materials. Andrew's paper has some appendices that includes a lot of the resources that are currently available. You know, Monika and Jim have a book. One of our co-panelists, Alicia Johnson, she has a group that's working on a Bayesian book at the undergraduate level. So I do think even compared to a few years ago, there's a lot more out there that if you're interested in getting started with, you know, teaching a Bayesian course at the undergraduate level, you're not on your own. You know, there's a lot of resources out there that you can use.
Great, Kevin. I'd love to turn a little bit to the mathematical prerequisites. And Kevin, I was pleased that your course is only hidden behind pre-calc, calc 1, interest at computer science. You know, but it's at the end of a long string of courses. And I think historically, statisticians have been terrible about not exposing students to the power and beauty of statistics until after a set of prerequisite courses from in mathematics and other kind of ways. You've talked already, Kevin, a little bit about some of those questions and how you've really loosened those prerequisites to a quarter of calculus and a quarter of of probability. Are there other ways we could be thinking about things that would still ensure that students have the right mathematical foundations to do the kind of modeling we're talking about?
Yeah, so I mean, I guess it depends on how far you want them to go. I know that, like I said, this is the third time I've taught the class, and every time I teach it, I try to scale back a little bit, do less calculus. So, I don't think I've done an integral all quarter, like at no point do I try to compute a posterior distribution by integrating anything. We write down a lot of, here's what the prior distribution looks like, here's what the likelihood looks like, let's multiply them together to see what the distribution looks like. So I certainly think that you can teach Bayesian statistics to students who have no background in integration. Again, like how far can you go? That's a different question. I think if you want to start talking about distributions, if you want students to be able to write down a beta distribution or something, they need some level of mathematical sophistication that they're comfortable with, writing e to the whatever, thinking about, I have a y and I have a theta, which one is being treated as the variable. But I view like everything from the perspective of just statistical literacy and intrastat. I mean, we get a lot of mileage in intrastat with never writing down the normal PDF. They deal with normal distributions, F distributions, chi-square distributions. We never write down the formulas for that. And so, why can't you do that in a Bayesian framework too? I don't see any reason why you can't. Again, this isn't how I've been teaching the class. I do think you need some foundation in probability. At Cal Poly, with courses only being 10 weeks, I do rely on them having that probability of experience. But I certainly think in a semester-long class, you could spend a couple weeks on probability and give them the background that they need. So I do think that you could get to a pretty rich course in Bayesian statistics, at least at the intro level, with very few prerequisites. I think Nick, when we were talking at the beginning, mentioned the middle school version of Bayesian statistics. And I don't know if it exists yet, but I think it's attainable.
Great. Colin, you've already talked a little bit about how you're kind of removing one of the prerequisites for the master's. I guess my question would be, say I'm a student in environmental science or political science or something else that wants to use this kind of stuff. And I think this is the people who are buying the Kilreath's book. Any thoughts on this question?
Yeah, I'm in complete agreement there. I think the more of the requirements we can get away, and like, if you look at the previous version of this course, the tower of prereqs that this sat on, it was calculus to multivariate calculus to probability to math stat to Bayesian theory. Then you can take my course. And like, I like those students. They're pretty mathematically good at that point, but I don't think they need all of those skills. We can cut out a huge part of that. And that's actually something I'm really appreciative of. The department at Duke has been thinking about that and trying to cut down and pare back those things to get to a more reasonable level so we can get students through these things and then do useful stuff. In terms of what that actually means, yeah, I'd never do an integral in class. I would like that the students have some idea of what that is, but it's not critical to anything we're doing. Probability is probably the most important thing that they see. And again, most of those probability courses depend on that and a little bit of calculus, but they definitely don't need multivariate to get a deep understanding. And I think probably a lot of us have found in these courses that what's taught in calculus and a lot of these other courses is pretty orthogonal to the intuition that we actually want the students to have. Like, I'd rather they spend more time with probability and less time with calculus, because that'll make the course better for all of us in terms of understanding what's going on. Taking multivariate calculus is not going to help them understand MCMC.
Yeah.
I think that's where we're going. I think the tooling matters a lot. Partly for me, it's about sort of learning intuition and understanding things. And I think that's a lot where things like JAGs and these higher level domain specific languages for the modeling works, because if you don't have to monkey around with the code and worry about transition probabilities, you can see what happens if I swap out a t for a normal. Like, what's the result? How does that change my conclusions? And I think that gives a really powerful thing that doesn't require a whole lot of mathematical knowledge to get to that point. So I think this stuff is very applicable to a wide body of students, and we can make it more accessible. again, I'm not going to be the one who cuts out the probability requirement to start with, but I think we can head in that direction, definitely.
Yeah. Monika, you get the last word on this question.
Yeah, I would just add that I think my approach is probably similar to what Kevin had. And in a sense that to me, I feel like it's very important for my students to actually know how to code a GIF sampler, even though soon after that, we're going to move to JAX or STAN or whatever. So I think in order to make students able to see how a GIF sampler can be set up, then certain probability knowledge, and then we can do the review, of course. And then, but regardless, I think, I guess to me, the goal as a elective course, I really want the students to know that instead of just using a one-line code using STAN GLM or something, that they can achieve it. But I agree, I think depending on the prereqs and the goal, I think we might be able to adjust, and then many of the computing tools as well as the understanding, I think, behind it, I think we'll be able to facilitate how we want to achieve it. So I'm actually really glad about all of the resources out there. And actually in the chat, I think many people are talking about like their great experience working with STAN in their courses or STAN packages in their courses. So I think, yeah, I definitely look forward to more resources and innovative ways of using them in our classes.
Yeah, and let me use that as a pivot point. It's a really good conversation and things going on in the chat. You know, there was one person who noted that they're curious why all three speakers use JAGs predominantly in their courses, as they had found STAN has a simpler and easier to understand syntax. There was some other kind of back and forth with that Alicia Johnson from McAllister has been using STAN in her course. And again, some of the different learning goals that people are thinking about. For Monika, thinking about this importance of describing models as opposed to just one-line code, and some of those other kinds of questions. I've certainly found it the case when I've taught some kind of, posterior distribution sampling. It's hard for students to understand really what's going on, even as they kind of go through that process. There was a follow-up in there about the thing that they responded liked best about STAN is how it arranges statements into blocks, data, transform data, parameters, transform parameters, model and generated quantities, and kind of found that forcing the user to put the STAN statements in the appropriate block makes it easier, in their opinion, to understand the code. But I'd be curious. I must admit, that's the thing I was found most surprising was the kind of JAG's focus of many of the panelists. And I think you've talked a little bit, but Colin, do you have any kind of further thoughts? Like, do you see that is what you're going to be teaching 5 years from now?
I'm not sure. I think JAGs is useful and it's not going to go away, but I think clearly the rise of some of these more modern probabilistic programming languages like STAN in particular within our ecosystem, but even things like TensorFlow and other things are important because of computational complexity and computability. Like, can I fit the model that I want, or am I limited by my tools? I think for most of us in our courses, we're probably not running into that too often. So it's less of a concern now, but maybe in 5 years, it's not. And you do have to think a little bit about the data sets and the models you're using, how big they are. But we always play that game in some sense of trying to optimize those. I would say the reason that I ended up on JAGs was partly because I found its syntax to be the simplest, and also it's the simplest thing to just sort of deploy across students' computers as well as servers and everything else. I do appreciate like the block organization within STAN, but I feel like that's an extra level of syntax personally that is a little bit harder to explain to students, and like they don't have a good mental model between like what's a distribution versus what's a discrete transformation and the data. Maybe using that is something that's actually better though, because it helps them sort it out and keep it clear in their head. For me, JAGs was beneficial just because it was the closest relationship between the text I would write describing the model on a slide and then the code I would then use to implement it. Like, and that may be a little bit tautological if I was writing my formulas to look like JAGs code, because that's how I do things. But I think that worked pretty well. There's certainly warts, things like parameterized in terms of precisions instead of variances. That constantly causes grief with students. If I could change it, I would. But again, it's things you can get around, and I think the benefits outweigh the costs. I don't think teaching STAN is at all wrong. Like, it's perfectly beneficial. It's fine. There are these bigger issues about sort of it being a black box. It's like, do I want to get into the conversation with my students about what Hamiltonian Monte Carlo is, or nuts is versus what's a Gibbs sampler? but I don't think they particularly have an idea what JAGS is doing either under the hood. But it's at least a little bit closer to traditionally what they might have seen when they were writing their simple like Metropolis Hastings within Gibbs type chain in their theory class. But again, I don't have a strong feeling there, but I think that's something just to keep in mind. When we gave a version of this talk discussion at JSM, there's things about, well, why not about variational approaches and things like that? And that's great. And if you can include that, but again, it's just getting even more complicated, more things you have to build on top of everything else that you're doing. So it's a trade-off.
Great. Kevin?
Yeah, when I first started teaching this class, I mean, 90% of what I do is stat ed these days. So I don't do a lot of Bayesian data analysis on my own. I don't personally know Stan, so I knew a little bit of JAGS, and I figured might as well go with that. And there are good textbooks out there. The Krutchke textbook has JAGS. I think it has Stan now, but so there are some resources out there. It wasn't a particular preference towards JAGS. It seemed to be a relatively smooth learning curve for students. When I've looked at Stan, I don't know it very well, but it does seem, at least at the level of what I'm trying to teach, it does seem to be a little bit steeper of a learning curve in terms of getting students started. I mean, if in my preference, if there was a nice suite of applets that did Bayesian statistics for you, did like all of the common models that I would want, I would probably have my students use applets and not have them do a lot of coding on their own. Again, like with my vision of this being more of an intro stat course. So yeah, I think, there's any statistics class, there's lots of things to consider when you're determining, how much computation, what language to use and things like that. I think JAGS is fine. I don't think it's necessarily the best approach or the only approach. And so, there's lots of reasonable approaches.
Great. Monika?
Yeah, I would just add two things. I mean, I think I told everybody I use JAGS, and I just responded in the chat that why I like it. But I would just add two more things into the discussion. I think one thing is that Stan, I agree, it could be really useful, but sometimes can be confusing. But one way to use it is, some of you, if you know about the Rethinking book, I think Richard actually wrote his own package that is like, it's a wrapper around the Stan, our Stan itself. So I think one way, if you really want to make it more accessible, but then utilize the power for computing from Stan, and I think that will be definitely one thing you can try. And then that book is awesome in that aspect. But I will also say that, like, for me, another reason to use JAGS and compared to Stan in particular is that, like, at the end, like in those case studies that I mentioned, I actually introduced latent class modeling, which actually involves discrete variables. And then Stan will be really hard to do it if many of you have done it. But then the syntax for JAGS, I mean, if I just share a little bit of the sample script of how to do like those latent class indicator and stuff like that, I think is pretty much intuitive for the students in the end to catch on it. So to me, I guess, but again, if I really want to teach it in Stan, I'm sure I will figure out a way to make it work in Stan as well. So just like, I just want to echo what Kevin was saying earlier, like there's so many resources and tools, and and it's great to have those innovative resources out there. So I guess then it's up to us how we want to use it. And I think it's going to be an ongoing discussion for years to come, I'm sure.
Yeah, no, I think that's very true. And it's good to see how active things are and these resources. Just a couple of kind of things from the chat. Someone had talked about how Stan can sometimes be challenging for students with minimal math stat training, with some of the nuances like the target equals plus statements when the model involves transform parameters. And I think that kind of gets at a handle. There's a lot of stuff going on here, a lot of concept thresholds happening. That same person, though, said they also do use Stan to teach non-stat majors. There's a kind of a good pointer to the tipsymath.org group, where there's a subgroup of individuals working on upper division pathways. This is the Transforming Post-Secondary Education Mathematics project that's really trying to kind of ensure that mathematics is engaged in some of these pedagogical developments. Obviously, since there's such a mathematical framework here, I think that makes a lot of sense. And then there's also kind of a question that's come in about Bolstad and Curran's book. the third edition, the Introduction to Bayesian Statistics, which they've noted introduces and compares Bayesian and frequent disinference. I think one of the things I found really valuable from the cluster of papers was that collation of resources, to see that there's such a kind of set of resources out there, and also many of them, particularly some of the things Monika had talked about, that are really focused on active learning and kind of best practices for STEM education. I guess there's one, my last question might be that one that's come in, someone thanking Monika for all the resources. They're teaching a Bayesian elective this semester at their school, and they're struggling a little bit to make the learning more active, and ask for any other ideas and suggestions for in-class activities besides the guided reading later in the semester that you described. You got any thoughts? Again, start with Monika, Colin, and Kevin. Jump in afterwards as well.
Yeah, thanks for the question. Yeah, for me, I guess, yeah, I was trying to use that example to see how, to illustrate how we can have the engagement. But I guess, well, this kind of active learning engagement could happen before, like they are ready to read articles as well. And I think that's why I think it's important to embed like computing labs throughout, and then maybe just doing the lecture time, and then you have those, like I would say, like to some degree, step by step of how to do the basic stuff, and then give them sample code, and then do that kind of analysis afterwards. And I also think case studies can actually happen early as well. Like for me, I wanted to cover enough models that they can do all kinds of things, but then another way that you can organize case studies that let students like work in pairs and then discuss and then debate to some degree maybe in class will be that you can say, if you cover one example for a particular model, and then you have another related example to show. And I guess they're not like super innovative, but I think there's definitely ways to engage students. And like I described earlier, I think trying to use discussion forum, now ever more important online, I think is going to be really helpful. So I wonder if Kevin and Colin had like in-class activities, guessing that was what that question was asking in particular, if you have any to share.
Yeah, I don't personally have a lot of like, I should be making my course more interactive and active. That's always a goal. I would say something that I take from some of the other courses I teach, which are sort of statistical computing courses, is I do a decent bit of live coding with the students, particularly when it's, say, teaching like the JAGS component, because that's something they haven't seen much before, and talking it through, doing the like either intentionally or not having errors, and then going through the debugging process. But I think a big part of, for me, is trying to get them to learn some intuition about like what should the result look like. And I think they have some difficulty with some Bayesian models in general. Just like, I don't know what the result should be, so they're not like sanity checking the results, see if it looks anything. And so going through that process in class, narrating it, doing things, breaking it purposely, and then saying what went wrong here, and then going back and fixing it is a very useful sort of activity. Sort of Socratic dialogue kind of thing. Ask them questions about what's going on. Don't just sort of show them the whole thing. I find that useful. It's hard and it goes badly sometimes, but I think it's more worthwhile than not mostly.
Yeah, I think, you know, I'm struggling to make my current class interactive in our online environment. I know when we're in the classroom, I do have students do coding in class. So, you know, we'll talk about the problem, and then I'll have them try to do it on their own. I also like to do lots of simulations, and this goes for probability too, but in my probability course, we do a by hand simulation every day, you know, with spinners and coins and things. And so, like, you know, when you're introducing MCMC, I generally do, you know, let's simulate a metropolis algorithm by hand. I think those tactile simulations are interactive, and they really help students see a little bit more concretely how some of these methods are working.
Great. Well, Kevin, thank you very much. Monika, Colin, lots of great ideas. All kinds of stuff that I wasn't aware of has been making its way into the to the chat. So feel free to save that. As always, we'll be recording, you know, posting the recording in a couple of days, as well as the slides for today and these other links. Again, here's the link to the cluster of papers. I just want to thank you all for sharing your wisdom, both with the Journal of Statistics and Data Science Education, as well as today, because there's exciting things happening, and I really appreciate your telling us about it. Have a great day, everybody. Thanks.
Thank you,
Thank
Nick.
you.
Everyone. Take care.